Just like before, there's something neat that happens with uh, angle bisectors of a triangle. They form another center, um, what we call the incenter. The actual theorem in your book is called the concurrency of angle bisectors of a triangle, but the point of concurrency, the point where all the lines intersect, is what we call the incenter. The angle bisectors of a triangle intersect at a point that is equal distance from the sides of a triangle. If I look here, this here is an angle bisector. This ray OK. This ray NK is also an angle bisector. This, I guess I really should be saying segments. The segment MK is also an angle bisector. They all intersect here at K, which is my incenter. Now, if I think about just this part of the triangle, from U to K to V to O, so just this part of the triangle, if I know that K lies on the angle bisector of point O, well, then that means I know it's equal distance from this side of my angle, and it's equal distance from this side of my angle. So this length and this length has to be the same. That's what the angle bisector theorem tells me. Now, if I only look at this part of the triangle, from T to K to U to N, so just this top corner, well, NK is an angle bisector. And K is on the angle bisector. So that means it has to be the same distance from the side of my angle both ways. So that means this segment TK and segment KU have to be the same. So this side, sorry, not this side, this length, and this length all have to be the same. And that's all that this angle bisectors, concurrency of angle bisectors of a triangle is saying, is that because of the angle bisector theorem, these lengths have to always, this point will always be equal distance from the side. And the really neat thing is that if I would draw a circle starting at K and has the edge placed on U, it will make an inscribed circle like this here. I actually have an animation again for you to see it, not just one static picture. But yes, the special thing about incenter is that the lengths from P to the edge right here will always be the same. So P to I is the same, P to L is the same, so on and so forth. This is not saying that P to B is the same by any means. No. P to C, not necessarily the same. Nothing says that. Alright, so what you see here are different color lines. These three in particular are what we call the angle bisectors. The way you know for sure they're an angle bisector is what's in this box here. It's 18.53 and 18.53, which is this angle right here and this angle right here. You know without a shadow of a doubt it's an angle bisector because I even reported to you the measure. Same thing over here. This angle right here, angle CBF, is 44.62 degrees, and same thing here. And last but not least, this box says it for these two angles. It's just to show you that these orange rays right here are in fact angle bisectors. And these will always be an angle bisector no matter how I move the triangle. These purple lines here, over here, this is where I have information. I show you that whether it looks like it or not, they are actually a right angle. They form a right angle with the side of a triangle. And the other thing is, they are all the same length. No matter where I move them, I get the same length. Alright, so that tells me that no matter where this is, from C to G, C to F, and C to E will always be the same. And again, the really neat thing is if I would take a circle and I would extend it from the center or the incenter here and brought it to the edge of the triangle here, I will get a circle that will always be located perfectly inside of this triangle. You could say it's an inscribed circle because it's entirely inside the triangle except for it intersects at the edge of the circle and only at the edge of the circle. Now this center, if I have an obtuse or an acute angle, I have never seen the incenter go outside. And as the name suggests, it always stays on the inside. The incenter is always inside the triangle. It's one of two centers that is always inside the triangle. Medians are the other one, which we'll learn in the next chapter. But yep, the special thing about the incenter is that it's the same distance from C to G as it is from C to F as it is from C to E. And what's even neater is if I hide all the objects. Alright, so at this point, let's apply what an incenter can do for us. If I look at this problem, it says find the values of length of segment GF, so from G to F here, length of segment GD from G to D, and length of segment FE from F to E. If G is the incenter of the triangle. Oh, if G is the incenter, then that tells me that this blue segment right here has to be an angle bisector of angle FED. So this angle here and this angle here have to be the same. Segment CG is an angle bisector of angle BCD. So this angle and this angle here are the same. Note, these blue lines aren't even close to being the same length. However, if I remember my theorem, right here, the angle bisectors of a triangle intersect at a point that is equal distance from the sides. What's that telling me? That is telling me is that G to F will be the same as G to B as G to D. So I'm going to draw this real quick, but you should be able to get at least two of the three ones that they asked about. So if I look real quickly, again, even though it's not drawn to scale here, sorry, it's a rough sketch by hand, I know that G is the incenter, which means these perpendicular distances all have to be the same. So if that's 20, this is 20, and this is 20. Oh, and look at that. That's two of the three I was looking for. At this point, the only thing I have left to look for is this side right here, segment FE. And if I think about what I did last time in the video with the circumcenter, if I see a right angle, what I'll probably be doing is looking at just a triangle that contains that right angle. So the rest of this here doesn't even matter for the last length I'm looking for. It's a right triangle. So I'm going to be using a squared plus b squared equals c squared. And if you remember, that's the legs of the triangle squared plus leg of a triangle plus the leg of a triangle squared equals the hypotenuse squared. So 20 squared plus x squared equals 25 squared. 20 squared is 400. X squared stays as x squared. 25 squared is 25 times 25, which is 625. Subtract 400 from both sides. You should get 225. And when you take the square root, you should get x to be 15. However, I'm not looking for x. I was looking for length of segment FE, 15. That's really about the difficulties of this problem. Either finding the Pythagorean theorem, a squared plus b squared equals c squared, or just saying, all right, what parts have to be the same? If you can do that, you've pretty much got this section down. So next time.